Good evening, sir.
So I'll keep it short. I will not tell you any big story. So Bohr's theory is again it's a model, okay, a model which was imagined by the Niels Bohr, and based on this model, he was able to explain most of the phenomena that atom was exhibiting, and it was one of an attempt to explain the discrete nature of light. So if we talk about atom, okay, it will have a nucleus and then it will have orbits, right?
Yes, sir.
Now, first of all, we need to understand this orbit is not a physical orbit as we believe. Okay. So although we have a theory which is supporting this theory is all about this circular motion and all, but Bohr's theory is actually about stationary orbits. And the word stationary is not representing this physical orbits. It is representing, of course, a space in which the energy is constant, the energy is fixed. And if we talk about the fixed energy level in a space, then the concept of standing wave or concept of stationary wave comes into picture. So here, to explain this standing wave characteristic or standing wave nature, we have to imagine about the wave particle duality as given by the de Broglie. So what did de Broglie or the de Broglie said that a particle can exhibit the wave-like character. So these electrons are actually exhibiting the wave-like character, and these wave actually superimpose. It is like imagine there is a loop. Imagine there is a loop. Imagine this is a loop, and you kind of struck the loop somewhere here to create a disturbance. And as a result of the disturbance will travel this way and will travel this way, and they will exactly meet here, right?
Yes, sir.
And after meeting, it will reflect back because let's say the disturbance is continuous, and this reflection will create another wave on the two sides, and this will superimpose with the incoming wave, and in turn, it will create the standing wave. And the property of a standing wave is that it keeps the energy of the space constant or confined. So of course, there is a conversion of energy from the potential to kinetic and vice versa. So this is the kind of analogy which we generally draw when we talk about the standing stationary orbit concept. Stationary orbit is here means the constant energy space diagram. Okay. And the word orbital we use in a context that the probability of finding the electron is maximum, right? So we have something called orbital, and these all are actually a mathematical wave which you think as an orbital, P, S, P, D, F. So these all are basically probability distribution graph. If you plot in a three-dimensional paper, sorry, three-dimensional space, uh, in a polar system or in a spherical coordinate system, then that is the shape in which the probability will grow or shrink or diminish or reappear. So that those shapes are basically the probability distribution graph. And every shape which you have seen for S orbital P, D, or F, and in D also you might have seen many other orbitals, the suborbitals DXY, DYZ, DZX, DX Y square, something. Those naming are actually meant for certain distribution of probability function. Okay, so probability is like we cannot see the world within the atom. We have only mathematical model for it, and these are probabilistic model, and that is where we have the probability, you can say, graph or a mathematical graph, and these graphs are called the orbitals. Okay, so generally we have a very wrong perception that these orbitals are again something like physical object. Okay, so these are not physical objects, these are ideas that you may find it on there or not. So the idea of stationary orbit is like a finiteness in the energy value. That is how we represent the stationary orbit, and how all this began actually. So this all began from the the curiosity to understand light. So much before the atoms, we were only curious about light. What is light? How it propagates? What is the origin of light? How fast it is moving, and so on. And in the due process of investigation on light, some experiment was performed, and the white light coming from the sun was actually sent through the chamber containing the hydrogen atom. And when the light passed through the chamber, then in front of the screen we got something called a spectrum, and this spectrum was called the absorption spectrum, because on the other side it was a bright screen but with some missing dark, you can say, pattern or like lines. So let's say you have a screen and you're throwing this flashlight, but when the light is crossing that chamber containing the H gas, on the other side you are not getting the continuous light, rather you're getting some missing lines, or a band of you can say lines are missing there. So that missing line was kind of some sort of significance. It was representing some idea that these particular energy values got absorbed by the H atom, and therefore those photons could not reach the other side, and that's why we got some missing lines. So the hydrogen spectrum that was obtained was a kind of proof that there is a discreteness, or there is a particularity in in nature of atom to absorb certain photon, and not absorb every photon. So they can only absorb photons which is having a finite energy to let the electron to move from the one stationary orbit to the next stationary orbit, or next to next. So it can only move between two finite energy values. So all possible values are not favorable by that term. So all possible values are not present in the atom. Atom is having the discrete energy structure, which is not seen, not known. We can only imagine that discrete energy structure, and you may give some creative shape to it, some artistic rendition of the same idea. And Bohr came with this rendition, this artistic idea of orbits. Okay, and luckily this, I mean, this turns out to be the revolutionary idea, because through this idea he was able to apply the Newtonian physics also to an extent. And after applying this Newtonian physics, he was also able to demonstrate the experimental evidence through mathematical, you can say, definition. So all these things came under the guise of understanding light actually, and the discreteness was a big concern, because the missing lines on the hydrogen spectrum was the first thing that intrigued Bohr a lot, that why these are missing. And he got certain values that were exactly missing in this uh, the spectrum called absorption spectrum. So those missing values he calculated somehow. I don't know how he calculated those mathematically. And he went to meet his friend. His friend was a mathematical genius, and his name was Balmer. And he gave these four values. That do you see some relation in these four values? And the Balmer within some time came up with a formula in which if you substitute to 1, 2, 3, 4, you will get all those four values. So one thing was clear, that these are discrete values, these are quantized values, and they only appear in some multiple of a value, a number, and therefore it's called quantized. Only you can only get those multiple of that simple value. And later on, this formula which Balmer gave was converted into a Rydberg formula, which is known to everyone. What is that Rydberg formula, right? So that is how it all is started. Okay, so that is how the Bohr's theory came into picture. So Bohr's theory is all about, understanding the discreteness in the subatomic world. So continuity is a phenomenon of the bigger world, and discreteness is a phenomenon of micro world. So in micro world, nothing is continuous. Continuity is a perception that we develop at a macro level. Okay. So for example, when you open the tap, you may think that water is flowing continuously, but if you look at the atomic arrangement, you know that H2O molecules are not touching each other. There's a molecular spacing, isn't it? And one is falling after the other. So the thing which appears continuous in our day-to-day life is not continuous if you try to observe at microscopically. So the word continuity becomes obsolete the moment you enter the microscopic world. So this distinction, the difference of the two worlds, the microscopic and the macroscopic, uh, is actually manifested by the discreteness and the continuity. And this is the essence of learning this quantum physics or modern physics, that we try to enter the world having a different scope, and in this world everything is discretely present, and therefore there's a different way to study, learn, and we formulate different laws for the same, and so on. Okay.
Yes.
So I think before Bohr's theory, many other ideas also came into picture. So you might be aware of the Thomson plum pudding model, right?
Yes, sir.
So in the Thomson plum pudding model, the positive and the negative charges were imagined, okay, much before today. So how they imagine that we have a positive charge and negative charge is spread just like the plum. The pudding. Pudding means what you feel, right? So
Yes, sir.
in the plum pudding model, they imagine that way, and imagine a person imagining atom in that way is getting Nobel Prize. That's how the world is started. Someone's imagination was admired to this extent that we got Nobel Prize. So in the Thomson model, we consider something like this. So imagine our nucleus is positively charged, right?
Yes.
So if this is nucleus is a positively charged nuclei, and electrons are also spread. You can imagine electron as an electron cloud. Electron as a something which is spread throughout in the entire volume. Okay, and when this electron which is spread in the entire volume, when this nucleus is there, to understand this model, what we do is we simply just I'll do once again. So what we are going to do here is we are going to shift. So I'm going to keep the negative charge like a complete, spherical charge. So let's say the negative charge is spread throughout, like spherically everywhere. And the positive charge, the nucleus is slightly displaced. Why I'm keeping it this way? Because it is similar to, thinking that the electron is moving around or getting attracted to this nucleus. Okay. So if I keep the nucleus slightly shifted from the center, with a distance r. Okay. What will be the force of attraction? Imagine the charge is
Sir,
we
but
have
was there any like centralization in Thomson model?
pardon?
Sir, like there was not any sort of center in the Thomson model, right, sir?
No, we are taking just exactly one electron and one this proton. Just
Okay,
one
sir.
and one. I mean, we have only one and one. We don't have many actually. Okay.
Yes, sir.
So in that case, if I keep the positive charge intact and so negative charge intact, and if I shift the positive charge, what will happen? They will attract each other, right?
Yes, sir.
So they are going to attract, isn't it?
Yes, sir.
Yeah. So what will be the attraction force between them?
Mm,
The attraction force between them will be how much? So imagine charges E and positive charges, let's say ZE. Okay. So imagine if we have a negative charge sphere, how we define the electric field within the sphere?
Sir, here are we considering a solid or like a shell sort of?
It's a solid actually. It's a three-dimensional solid sphere.
Okay, sir.
So within a solid sphere, if a charge, let's say electronic charge E is spread throughout the volume, the electric field kinetic rho r by 3 epsilon, right?
Yes, sir.
So if I call this charge as ZE, imagine we have charge ZE. Just take a look. And if this negative is E, so force will be the rho will be how much? So the rho here is E by 4 by 3 pi r cube.
Yes, sir.
This is capital R. Okay, so we can think this way, isn't it?
Yes, sir.
And then we can say the force will equals to uh, is ZD into E, right? The electrostatic force, isn't it?
Yes, sir.
So and rho is so the force turns out to how much? You can see force is proportional to R, right? So it will have frequency of
Yes.
oscillation. This is like a SHM equation, right? So acceleration
Yes.
equals to how much? Mass of
The
let's take
nucleus.
nucleus. M. Just write M. It become ZE square by and therefore if you compare the omega square becomes you can imagine this is the omega square so you can get the frequency, right?
Yes, sir.
So a question like this may come in electrostatics by creating something like this material. So I mean,
Okay, sir.
this was a question. I mean, a complete question. So I need to check the question exactly.
So this sort of question actually came in one of the previous years, sort of.
Yeah, maybe. So you can expect question like this in the advance at least. It might not
Okay,
have
sir.
come, but you can expect. Okay.
Yes, sir.
See, in Bohr's theory, we have to deal with the discreteness. That's it. And
Oh,
discreteness here means discreteness of energy values. And the physics will tell you that if you want to create some energy value, I mean, discreteness of energy values, you have to set up something called standing or stationary wave. And every matter will exhibit the wave-like character. So you can think that a matter will exhibit a wave-like character, and with that wave-like character, you can establish some standing wave. From there, you can deduce some relation. So, what are the basic postulate of Bohr's theory? What are the basic postulate of Bohr's theory? Tell me.
so in an atom, there were stationary circular orbits
Electrons are only permissible to rotate
in those orbits.
in an orbit whose energy is constant, called
Yes, sir.
stationary orbit, right?
Yes, sir.
So that is the first postulate, and the second is for every orbiting electron, the angular the angular momentum of orbiting electron must be quantized. It means you cannot have any value of angular momentum. You will have only some definite value or its multiple. So this is called quantization of angular momentum, right?
Yes, sir.
So these are two theory in Bohr's, I mean, postulate, which is the assumption like angular momentum is quantized and electrons cannot move in any orbit, but they will move in an orbit whose energy is constant. Therefore, even while moving in the orbit, they will not radiate the energy because they have constant energy.
Yes, sir.
So what Rutherford said that no. Rutherford said that every uh, electron which is rotating in the around the nucleus, because of the classical theory of physics, it should radiate energy because it is accelerating charge and every accelerating charge radiates energy. And therefore, the orbiting electron should eventually collapse with the nucleus, and hence it should make the nuclei unstable, hence the atom. So no atom can exist in stable form, which is against the experimental evidence that we do have atoms which are stable, and therefore the Rutherford theory got rejected. That is the history behind the rejection of Rutherford theory. The classical physics do not support that Rutherford model. Okay. So Bohr said,
Yes.
Bohr said that the classical physics itself is not valid. So to overcome this, you can say controversy, Bohr said, the world, the Newton, which Newton believed, is not actually applicable in its entirety. We have a different world altogether, and this new world will have its own law. Okay. And that is perhaps the birth of the quantization, quantum physics, and all. So quantum, the word quantum is something which is finite, something which is discrete. So a finite value of energy we call quanta, and so the word quantum came into picture, and hence the quantum physics got a, I mean, separate, you can say, prominence as a separate concept branch, and people started investigating more on this. And then atom is having the both worlds. It means atom is quantized in some way, and it is also exhibiting the Newtonian behavior also. So how things are changing, and there is a theory called the Bohr's correspondence theory, in which as the quantum number becomes larger and larger, the the reality shift towards the classical world, the world which Newton envisioned actually. But as you go to the lower quantum state, it means as you move closer to the nucleus, the world do not follow the Newtonian physics. It goes to the quantum physics way. Okay. And you can think that Bohr's theory is the first milestone to establish this quantum world theory into practice. Okay. So quantum world was kind of developed by Bohr. I mean, he was one of the pioneer to the proponent of quantum world, quantum physics, and things are not same as we believe it should be. And because of this quantization theory, the instability issue was resolved, because the instability issue arises because of the assumption that we have accelerating electron, and so any accelerating charge must release energy, must radiate energy. But in the quantum world, what he is saying that, see, the electron is behaving as a wave, and the wave is here standing wave, which is maintaining its energy, and so the energy is quantized. There are many ways to understand this. So I'll give you the proof of the quantization of angular momentum. And so if I start with the same philosophy, if I hit it and if I create a wave, and the wave will move on both sides. Okay. And as the wave will superimpose from the reflection, it will create a standing wave pattern over this periphery or the circumference or the space and so on. Like this. And therefore, as a result of this reflection, we have a clear-cut standing wave formed. And if I take the radius of this particular orbit as r, because as you go away from nucleus, the size of the orbit will change, right?
Yes, sir.
So I can say that in a half perimeter, which is pi r, it must contains the integral number of wavelength. You can say n. It must contain the integral number of the loop formation. You can count the loop 1, 2, 3, 4 like this, and every loop will have how much value? So every loop will be, if you look at the nodes, this is called node. So between two successive nodes, the gap is called lambda by 2, if you remember.
Yes, sir.
This is n lambda by 2. But this lambda represents what? So here lambda is representing the de Broglie wavelength of the orbiting electrons. So lambda here is
Sir, I'm a bit confused about the timeline here.
which timeline?
Sir, de Broglie wavelength had already come by then.
So this lambda itself is de Broglie wavelength. But this wavelength, see, de Broglie is for matter, right? What is the matter here? What is matter here?
Sir, So here electron is behaving wave. I'm like a
Correct.
wave.
So that's why the lambda is coming for electron only. So that's why I'm saying lambda here is de Broglie wavelength of energetic electrons.
Okay, sir.
So what you're confused about? Tell me.
Sir, I'm confused about like, did de Broglie come by then? I mean, like, wasn't he in a like a later stage?
Okay. I got it. Yeah. So definitely, I mean, things have come in a different way. So in time of Bohr, he imagined this theory that the angular momentum must be quantized, but the proof came later on. In
Okay.
physics, many things came as a part of intuition, and then later on the proof came. So they said light was a, I mean, wave. So this idea came much before, in the time of Huygens, but almost 100 years later, it was Thomson, a Young's, who performed the, Young's, sorry, it was the Young's, Thomas Young, who performed the double slit experiment to prove that it's a wave. So imagine an idea and its proof. So when we are deriving some proof, of course, it may be in the future of the, you can say, assumption. So the postulate means it is your strong hunch, right? So
Yes, sir.
the postulate itself is assumption. So when someone is assuming, then proof will come later on, right?
Yes, sir.
Okay. So I mean, your doubt was very much genuine. I thought something here is doubt. The timeline is correct.
Okay, sir.
Yeah. So now, this is de Broglie wavelength. So I can say lambda d by 2. And the lambda d we can write is h by p, right? The momentum.
Yes, sir.
And therefore, you can say 2 pi r is n lambda, right? N lambda d Broglie. So this is the first way of writing the Bohr's quantization theory. You can write this way also. And then you may write like this. So you can say P into R equals to NH by 2 pi.
Yes, sir.
And this is the L, right?
Yes, sir.
So this is how you can prove. This is very easy to prove, right? Using basic physics.
Yes, sir.
Now, once you have the angular momentum, you may express the energy in again in a simple fashion. So we have a kind of a nucleus which is at rest, and electrons are only moving, and therefore you may write the kinetic energy equals to how much? So kinetic energy in rotational data is L square by 2I, right?
Yes, sir.
And it's very easy. I mean, see, once you learn how to write energy in a different form, it's really easy to express. This is actually n square h square by 4 pi square. And the I is mr square. The m is the mass of electron in r square. So the kinetic energy turns out to be how much? N square h square by 8 pi square m r square. So this is also one way of writing the kinetic energy. The other way will come from the Newtonian physics. Okay, so circular motion part. So there are many ways of writing things. So we know that if we have a orbiting electron under the attraction of a nuclei, so we have to use the Coulomb's law, right? Now the
Yes, sir.
question is how to write the Coulomb's law here. Should we write the Coulomb's law or should we write the electrostatic force? What we should write, which is better or more accurate?
Sir, the electrostatic force.
Yeah. So if R is the distance, this is ZE, then I can say the force on electron is basically we have to apply the formula Q into E. This formula is actually formula for force. We should not use the Coulomb's law. So don't use Coulomb's law, use the electrostatic force, because here the charge experiencing the force is not static, right?
Yes, sir.
Electron is in constant motion around the nucleus. So we should not apply the Coulomb's law between the nucleus and the electron. Okay. But the electrostatic force means under the influence of field of nuclei, this electron is moving and therefore it is experiencing this force QE, and this electrostatic force we can write as E times electric field is ZE upon KQ by R square, right? Right?
Yes, sir.
KQ by R square, that's it.
Yes, sir.
And therefore, because this electrostatic force will be equals to the centripetal force, so this we can write as mv square by R, right? Correct?
Yes, sir.
Where v is the velocity of the electron. And therefore, if you compare, you can say ZE square upon 4 pi epsilon naught R square is mv square by R, right? R gets cancelled. So you can see if I want to write half mv square, what is the answer? So you can see there's another way of writing kinetic energy from the Newton's theory. And because there are two ways of writing kinetic energy, one this way, another is this way. So both can be compared, right? Because eventually it's the same answer.
Yes, sir.
So by writing the Ke from the Bohr's postulate and Ke from the NLM part, we can actually get a very nice relation for the radius, right?
Yes, sir.
So what we have answered here, n square h square.
Sir, in the first case, how is the radius like definite?
No, where is it different? It's for a given radius, this is the answer, right?
All right. So, sir, we are like assuming that okay, R will be the radius at that
Yeah,
point.
at that point, correct. So this could be any radius, I don't know. Okay.
Okay, sir.
And this is basically R of the nth orbit. I don't know which orbit. So it's nth orbit. But I'm not writing n just to make sure it's easy to write. Otherwise, it will come. Here, me is the mass of electron. So again, I can drop the subscript E also. Okay. So E is like subscript, okay?
Yes, sir.
Okay, fine. So what is the answer here? N square h square by 8 pi square m r square, right? I'm
Yes,
not writing the subscript because just to make it easy. And from the Newton's law of motion, I'm getting 8 pi epsilon naught r, right?
yes, sir.
So 8 pi gets cancelled. Nice. R gets cancelled. So how much R we are getting? Epsilon naught n square h square. Correct?
Yes, sir.
By
By ZE square M.
this we can further write as epsilon naught h square by pi m e square into n square by z. So generally we take the variable only as n and z, rest is constant, we think as constant. And this is called the A naught. Okay. So what is the Bohr's the smallest orbit? It's a radius of the H atom in the ground state, right?
Yes, sir.
And the answer is epsilon naught h square by. Let's try to calculate this, because see, in modern phase, one practice that one should do is the calculation. I mean, you should always do it and realize for the first time that how these things are coming. And also we'll get to know that what kind of calculation mistake can perform, I mean, probably can make in the examination. Let's try to calculate this value. So, what is, how to write epsilon naught? I mean, of course, we know the value, but 1 by 4 pi epsilon naught is 9 into 10 power 9. So basically, epsilon naught we can write as 36 pi. Correct?
Yes, sir.
Now, why I'm writing this way? Because that will help me in okay. So now I have this answer. Okay. And pi into pi become pi square, right? And
Yes,
pi
sir.
square is roughly 10. So we can say 10 power 10. So now this becomes 1 by 36 into 10. And now I have something interesting. H square by me square. Okay. And do we have any option, or we have to substitute the value? Can we do something here?
I don't think so, sir.
Yeah. So we have to only do the calculation. Okay, anyway, I think then it's good to do all calculation. Let me do this calculation only directly. Anyway, so 8.85. Do you remember the value of epsilon naught?
Sir, minus 12. I mean, the exponent.
Correct. Now, if someone has got the patience of writing all these values, then you can do the calculation also. So it is roughly 8.85 into 6.626 whole square upon 3.14 into 9.1 into 2.56. And then we can take the all power together. So minus 12 minus 68, right? Plus 31 plus 38, right? How much is that? This is 19. So how much is that? 68, 38 is minus 30, and plus 31 is 1, and then minus 12 is minus 11, right?
Yes, sir.
Minus 11 is there, but anyway, what is the value here? So 8.85 and 9.1 is roughly same. So let's cancel out. Okay. And then 2.54, it's like 1 quarter. 2.5 is like 10 by 4. And 10 by 4 into, okay, this is 0.75. So 10 by 4, and this is 3 by 4. I mean, 10 by 4, then this is 3. 30 by 4, 7.5. And then it's 36. Okay. How much it is coming? If you do the exact calculation, let me do this calculation.
Sir, in a calculator?
Yeah, calculate.
Sir, I'm getting 5.311.
Yeah, very good. So 5.31 10 power minus 11, which is a meter, right? So this we can write as 0.53 angstrom, right?
Yes, sir.
And if you remember, the answer is this much only, no? 0.529.
Yes, sir.
So that's coming. So now you know that 0.539 has come from here. Okay.
Yes.
And that's why we can derive every formula in Bohr theory, especially in JEE Advanced. If you do not know the derivation, it is always difficult. And the first thing is always start with the kinetic energy, right, in two ways. One using the Bohr's postulate, and other using the Newton's laws of motion. Equality. The first answer is always important. So at least you will get the proportional relation. Even if you don't know what is A naught, what you can say R is proportional to N square by Z, right? And generally in examination,
Yes.
you're supposed to compare the radii for the two atoms and for two different the quantum number, right? N value.
Yes.
Now, once you know the radius, everything else can be determined with ease. So what else you can do is you can think of energy relation. So to know the energy of electron will be how much in the nth orbit? It is the kinetic energy in that orbit and potential energy, right?
Yes.
And what we know that kinetic energy we know is Z square by 8 pi. This is the answer. If you remember, this was the answer, right? Yeah.
Mhm. Yes.
So this answer is important. Okay, always write it from the laws of motion. Because
Okay.
laws of motion will get all the answer. And potential energy, we have the formula minus K Q1 Q2 upon because this is K R. That's it. And what you can realize that everything depends on R only. So because we know the answer for R, everything is easy, right? In
Yes.
fact, I mean, this is something which we have done before also, but in fact, you can realize that the total energy, if you add the and if the total energy also turns out to be negative, right?
Yes.
What one must remember that En is basically everything we can write in terms of potential. It's a half of Un, correct?
Yes.
And it is mod of, I mean, sorry, it is minus of Kn, right?
Yes.
Now, why I'm writing like this? Because this formula is easiest to derive, right? K cumulative by R.
Yes.
So every other answer you can get from here only.
Yes.
Then you're not supposed to solve anything. You can get all answer from here itself, right?
In exams, yes.
No, everywhere, even in derivation also you can do it fast. Because this is the relation and the negative, you see, listen. If the total energy is negative, we call bound system. If the total energy of system is negative, it is always called the bound system. And the property of bound system is it is mutually governed system. I mean, it will always remain in that way. So we are not supposed to think about how to bind the electron with nucleus. Nucleus will hold the electron the way it is holding forever because the overall energy is negative, which means they are kind of under the debt. So they have released a large amount of energy to become what they have become today. So if you want to destroy, if you want to separate the elements, the protons, electrons, neutrons from each other's attraction and all, then you need to supply energy equals to the bound energy in value And once you supply that energy, you will kind of destroy the system. Every negative energy system is kind of a stable system, and if you want to make it unstable or destroy, you have to supply that negative value, equivalent value energy. So let's say if the bound energy of some system is minus 10 joules, so to destroy, we just need 10 joules. That's it. Understood?
Okay, sir. Yes, sir.
Okay. So how much energy we need to destroy the Earth?
Sir, I think we can solve it by using the self-energy concept.
Very good, very good. Yes. So what is the energy of self-energy of Earth?
Sir, I remember only the electrostatics.
It's the same thing. You can convert
Yes, sir.
mass into
Analogy.
energy. Yeah. So what is the formula in electrostatics?
Sir, 3/5 G_m by RE square.
But the energy is negative, right?
Yes, sir.
So to destroy, we need this much value, correct?
Yes, sir.
Yeah, so that's very good. So you still remember this? So you know that how much energy we need to destroy anything, right?
Yes, sir.
So anything having negative energy as a whole can be destroyed with providing the energy sufficient to make it zero. Okay, that's called the destruction of the system. Now, what are the benefit of writing this way? Because we know the R itself. So we can write the En directly, right? It is minus ZE square upon 8 pi epsilon naught R. But R itself was epsilon naught H square by pi ME square into N square by Z, right?
Yes, sir.
And therefore, you can see something here. The En turns out to be minus ME power 4 upon 8 epsilon naught square H square, right? And then Z square by N square, isn't it? So simple. Correct?
Yes, sir.
This entire term we generally write as RHC. Okay.
Yes, sir.
And the RHC we write as 13.6 EV. The electron volt way of writing energy. So now again, this is something which one should know this answer. RHC is 13.6. Okay. Now, what is really important here to understand, learn, is called the R infinity. What is R infinity? This is called the Rydberg constant.
Yes, sir.
And basically, this R infinity, HC is ME power 4 by 8 epsilon naught square H square. So basically, R infinity is how much? So this is the formula for the Rydberg constant. And out of 8, this H is constant, C is constant. So E is constant. So R infinity is proportional to mass of electron. So generally we say mass of orbiting object like this. Okay. Like this. Okay. Now, why I gave this particular proportional relation, that will become clear very soon. So now what is the R value? So we know that the Rydberg constant value is how much? I think 1.110 per power 7, right? Meter inverse. So dimensional it is inverse of length, right?
Yes, sir.
And you can see clearly SC by lambda is called energy, right?
Yes, sir.
So R is like 1 by lambda dimensionally,
Yes, sir.
isn't it? So this is the R infinity value. Again, that is supposed to be remembered, because if it's easy to derive, SC itself is how much? Because RSC is 13.6, because this is easy. And we know that SC we can write as 1240 EV nanometer.
Yes, sir.
So EV gets cancelled. So what is R infinity? 13.6 by 1240 nanometer, right?
Yes, sir.
Sorry, plus 9.
Plus.
It is plus 9, correct?
Yes, sir.
And
Yes, sir.
so it is like 1360 upon 1240, 10 power 7, right? And 1360 upon 1240 is how much?
Mhm.
It is 1.09. That's a more accurate answer. Okay.
Yes, sir. Sir,
So
can you
this,
just come back in a minute?
yeah, sure.
Sir?
Yes.
Yes.
Now, why I'm doing all these calculations? Because you can see that how calculations are done, how one should substitute the value, and how to get the answer very fast. Okay. So in modern physics, it is also necessary to learn the way to substitute the value and solve the question. Sometimes calculation becomes really cumbersome, and many students feel it's really difficult. So you have to learn all those things and remember the basic. I hope this is okay.
Yes, sir.
Now, you know the energy for the uh, total energy, and you got how much En equals to RHC, right? And it was Z square by N square,
Z
right?
square by N square. Yes, sir.
And we know kinetic energy is how much? So simple, right?
Yes, sir.
And so we can write as half mv square, where v is the speed actually.
Yes, sir.
And so you can see clearly that the velocity is nothing but see, even nothing is required. When what you really need to know is that this relation, that what is the speed proportional to. That's it. This is speed, right?
Yes, sir.
And also dimensionally, we could have said this answer directly because energy is Z square by N square. So speed is square of energy. I'm sorry, energy is square of speed. So we have to take the square root of this number, right? So anyway, this is the answer. And if you exactly calculate this value, the answer will be how much? Is 2.1 10 power 6, right?
Yes, sir.
How much is this? I don't remember. I think. So you can again do the calculation and get the answer for yourself. So you can do many more things like, and at the end of the day, what you are really supposed to remember is the proportional relation. That's it. And what about this omega? So V equals to omega R. Okay. I hope you remember this answer, right?
Sir?
You remember this answer,
Yes, sir.
and now you can see it's omega n is how much? It is 2.1 by 0.53, which is roughly I think 4 point something, 4.2 or something, 4.1. Okay. So 2.1 divided by point, oh my god, 2.53 is 4, roughly 4, 3.96. So I'm going at this is 4 into 10 power 16, right? Z square by n cube, right?
Sir, I'm not sure about the constant in the velocity.
Okay, this is the answer, but anyway, I am sure about the constant in the velocity. So
Okay,
you're
sir.
not supposed to be constant. I mean, know this. I mean, generally they give the answer, or if it is not given, it means they will not use it. What they really want is the proportional value, which you should remember. Z by n, Z square by n square, and so on.
Yes, sir.
Okay.
Yes, sir.
And then time period is 2 pi by. So it is 2 pi by let's make it a frequency. Just time period is not required. So let's go to the frequency. It is omega by 2 pi. So 4 divided by 6.28 is I think this is fine. So these all are formulas, right?
Yes.
And then the last one once again, the energy we wrote as minus 13.6 in terms of value. Z is square by in electron volt, right?
Yes.
Okay. Now, when an electron will transit from one orbit to another orbit, let me tell you, even you can excite an electron from the low to the high energy, it will not remain there for long time. So the time to stay in the high energy orbit is very, very small. It is 10 to the power minus 8 seconds, which is like there is no time, it will come back immediately. So you may excite, but it will not stay there, rather it will come back in almost no time. Understood what I'm saying?
Yes.
Okay. So all will come back to the ground state. And whenever the electron will jump from the high energy state to the low energy state, it will always release the energy, because the difference of energy is not kept by the atom, rather it is released back, and it goes to the in the form of electromagnetic energy. Okay. So whenever there is a transition of electron from let's say M to N, I think N to N. Yeah, fine. So as a result of transition, when you go from the high to the low energy, it will be released as a form of electromagnetic wave of either certain frequency or certain wavelength. Okay. So you can say the way you want. And therefore, we know the energy of the mth orbit, right? How much? And energy here is how much? So which is at high energy? So the delta E loss is how much? Correct?
Yes.
Because I'm writing loss. So the energy difference will always, because once electron will come to the low energy orbit, it will have the energy of same as that of the orbit. So the extra energy which you had when you went there, that energy must be released back. Okay. And therefore this turns out to be how much? 13.6 is Z square like this. Or you can also write this as minus RHC formula. So the delta E loss so there is a reason why I'm writing like this, because the delta E loss you can write as SC by lambda, the wavelength release, right?
Yes, sir.
And this becomes the Rydberg formula, which is very famous. So 1 by lambda is how much? It is RZ square 1 by. So this is called the Rydberg formula, right?
Yes, sir.
And the R with subscript infinity I'm writing because here the assumption is that nucleus is not at all moving, as if it is infinitely heavier than the electron. So when we derive these formulas, this is the underlying assumption that nucleus is not at all moving. What is moving is only electron. Okay.
Yes, sir.
Okay. And because of this particular assumption, the word the subscript infinity is used. But what if things are not as we expect? So I'll come to that. What if? So all derivation will change. If I change the assumption, then I have to change the derivation as well. Okay. Okay. So we'll talk about the energy values in a way. So let's talk about the values, which we should remember that energy of the nth orbit is 13.6 into Z square V square EV, right? So for H atom, Z equals to 1. So the energy for H atom is very easy, right? Correct? It is 13.6 by N square EV.
Yes, sir.
So in order to be good with solving numerical, we must remember the values. This is 1, 2, 3. So the energy here is how much? Minus 13.6, right? Of course, in EV.
Yes, sir.
The energy of the second is how much? Minus 3.4. Correct?
Yes, sir.
Then this is 1.51. Right?
Yes, sir.
This is 0.85.
Yes, sir.
This is 0.54. Three 7, 2 7, 2 1, 1 6, 1 3 6. I hope these are the values, right?
Sir, I remember only till 3 7, sir.
So I think that is sufficient, but you can remember all of them. It's so easy. So 13.6, 3.4, 1.51, 85, 54, 37, 27, 21, 16, 136. Easy? Say
Yes.
with me. Okay, so 13.6, 3.4, right? This is something common. 1.51. Then all the decimal values you can write as 85, 54, 37, 27, 21, 16, 136. Close your eyes and try to say it once.
Okay, sir.
8554 3727 21 16 136.
Yes, sir. Got it, sir.
So if you practice once or twice, you can remember all values. It's so mysterious. You know, these values are so interesting that I studied for only once and I still remember today.
Yes,
So
sir.
I studied only once in the year of 2000, I think 3, exactly 20 years back. But there is something magical. I mean, I don't know, but I still remember the values. And I believe that everyone should remember these values. If you really want to master the board theory, first you have to master these numbers. So again, close your eyes and try to recall 13.6, 3.4, 1.51, 8554, 3727, 21, 136, 16, 136. Correct?
Yes, sir.
Can you recall all?
Mm, sir, let me first try once in my head.
Yeah, right.
Sir, yes, I recorded, sir.
So I don't think it's difficult, right?
Yes, sir. It's pretty easy.
Yeah.
I'm not sure about the pattern, but
It is something nice to brain, right?
yes, sir.
So it means these numbers are something magical. So
Mm,
I always say these are divine numbers, the numbers which we don't know why this is, although it's very cumbersome, but it still looks easy to the brain.
yes,
And
sir.
there is a continuous decreasing value, and there is also rhythm. You can also see the rhythm. 13.6, 3.4, 1.51, 8554, 3727, 21, 16, 136. And then you can put the number, decimal, EV and all. Okay.
Yes, sir.
Now, why these numbers are important? Because once you remember these numbers, for any H-like atom, the only thing is the multiplication by Z square, right?
Yes, sir.
Because the difference is only Z square, isn't it? So if I want to write for the helium plus, He plus, I have to only multiply with 4 to every value, right?
Yes, sir.
Isn't it?
Yes, sir.
Okay. Okay. And looking at the values, you can easily say what is the potential, what is the kinetic energy. So potential is how much? Potential is
Mm,
half of,
Twice.
twice of the total.
Yes, sir.
And kinetic is same as total, right?
Yes, sir.
So you can see that everything can be answered with only one answer. So now you know the potential, you know the kinetic energy without solving. And even more interesting is that if you know the kinetic energy, you can exactly answer the radius, isn't it?
Yes, sir.
Because I remember that the kinetic energy we can also write as n square h square by 4 pi square upon 2 mr square, right? Something like this. No,
Yes, sir.
this is not required. Or also we had we had a formula that kinetic energy is z square by 8 pi epsilon naught r, right?
Yes, sir.
So of course, if you know the k, you can find r, isn't it?
Yes, sir. So then we have to remember that constant value.
No, no, no. I mean, anything which is complex in the examination, they will give you. Okay, so they will give you the values which you can substitute eventually and get the answer. No need to remember all this. Yeah, but these values I always tell to my student that you must remember these magical values. So close your eyes and try to recall once again. See if you can recall.
Yes, sir. 13.6, 3.4, 1.51, then 8554, 3727, 2116, 136.
Very good. So I think while you're saying, you were closing your eyes, right?
Yes, sir.
Very good. So once you know these magical numbers, you can do a lot of things. So we need to remember certain things like energy of excitation. What is energy of excitation? You write as E1, E2, and so on. What is energy of excitation? It is the amount of energy required to raise the or transit the electron from ground state to the excited state. It means the transition must happen from ground to any other orbit. So E1 means energy required to raise, take the electron from ground state to the first excited state, which is the second orbit.
Second.
Understood?
Yes, sir.
So the beginning is always 1 in each case. But here the transition is to M, which is 2, 3, 4. So you can see that when I say first excited state, it means it is the second orbit. So whatever excited state I say, it is that plus 1 orbit, right?
Yes, sir.
And we know the energy of both the orbit. And therefore, if you go from 1 to 2, you go from 13.6 to 3.4 in negative sense. So you go from 3.4 to 13.6, right?
Yes, sir.
So what is the energy required here to go from here to here? So this is basically the EI is nothing but the energy of the M minus energy of the N. That's it.
Yes, sir.
So actually, you will get 13.6 minus 3.4 EV, right? And it is
Yes, sir.
10.2.
Yes, sir.
Always remember that the E1 is the biggest one because the difference will keep on coming closer and closer. As you can see, as you go higher in the orbiter, the two consecutive orbit will have not a much difference left, right? The difference becomes, it shrinks, isn't it? Hello.
Sir, E1, then E2 will be like 1, 2, 3 means it will be much greater, right, sir?
Yeah. I'm saying, of course, the first two will give you the in a way difference, but second, the 2 and 3 will give you less difference, right? 3 and
Yes,
4
sir.
even less, 5 and 6 even less, 7 and 8 even lesser and lesser. So as you go up, the difference from the next consecutive will be less. Yeah, from the first it is always going to grow, but the growth will not be much. So from 1 to 2, 10.2, but 1 to 3, it will not go become 20 or something. It will remain something close to 13 only, or less than 13, right? Because 1 to infinity is 13, right?
Yes, sir.
So the maximum is fixed. So any answer is going to be 10.22. isn't it?
Yes, sir.
Can we go beyond this? The answer is no. So if you take the ground state electron out of the atom, how much energy you need to give?
Sir, 13.6.
That is also called the ionization energy in this case, because we have only one electron system.
Yes, sir.
But this will become infinite excitation energy. We are exciting to the infinity level, like infinite orbit, right? The
Yes.
last orbit. Now, anyway, so what is the second excitation energy? E2. It is E3 minus E1, right? So E3 is how much, if you remember?
Sir, 1.51.
And the answer will come 12.09, right?
Yes.
Now, these values are not something which you can forget. You have to remember these values, then only you can master this chapter. It is so
Yes, sir.
famous that one should remember all the time. And this
Yes,
answer is
sir.
again famous. Okay. And E4 is how much? How much?
Sir, 0.54.
So this is 13.06, right?
Yes, sir.
So you can see that the moment you see these numbers, you should know which excitation energy we are talking about. And these three numbers are very famous in the chapter of modern physics, especially the Bohr theory. You have to guess the orbit from looking at the number. So 10.2, 12.09, 12.75 are the three famous numbers. 1, 2, 3. So 10,
Okay, sir.
12, 12. How to remember? 10, 12, 12. 2, 9, 75. So 2009, it's like this. How to remember? 10, 12, 12. 2009, 75. The decimal. Can you remember this?
10, 12, 12, 2, 0, 0, 9, 7, 5. Yes, sir.
Yeah. So 20 because 10.2 is 20.
Yes, sir.
09, 75. But anyway, you can also get the answer by subtracting at that instant, but it's good to know these standard values. So again, if you want to master the Bohr theory, you should master these numbers. Okay. So these are
Yes,
the
sir.
basic requirement for the Bohr theory. One must be knowing these numbers. And by looking at the number, you can definitely answer it. What is the energy of ionization?
Sir, 13.6 electron volt.
No, energy of ionization.
Sir, it is the energy required to like take an electron from the ground state to infinite orbit. I mean, like infinite orbits.
No. Energy of excitation is to remove the valence electron, the last electron from the valence shell. But in a single electron system, the electron itself is valence shell, right?
Yes. Oh, okay, sir. Like in general context.
Yeah, in general context, it is always the energy required to remove the valence shell electron, not the all
Yes.
electron, right?
Yes, sir.
And in the context of H like atom, it happens to be the same electron. Okay. So the energy of excitation to the infinite level is same as the energy of ionization. And the definition remains same. And if we have more than one valence electron, then we have the ionization energy 1, ionization energy 2, and so on. Okay. Because once you remove the first, then the remaining two will become the valence shell, and then the atom is no longer neutral; it will become ionized, kind of ion, and then to remove the next electron is much more difficult task. And then we have something called the half-filled and fulfilled orbital concept. So sometimes I1 is more than I2, right?
Yes, sir.
When it is more than I2, generally as we remove the electron, energy will required will increase, but sometimes it is decreasing also. So that follows
Sir,
the half-filled fulfilled concept. That if I remove an electron and it becomes half-filled, exactly half-filled, it
so
will be
it
more
means
stable.
stable.
Yeah, more stable configuration. So therefore, it will have it will be very happy to release. Okay.
Yes, sir.
So general and half-filled, fulfilled concepts are again different. You should careful about the half-filled and fulfilled as well. So these things are generally taught in chemistry. In physics, we go through some more rigorous ideas. Okay, so we have the ionization energy. It is the energy required to remove the valence electron, the outermost electron from the atom. Energy of excitation is different, right? I hope so. This is clear.
Yes, sir.
And an atom, when interact with photon, then there are only two types of interaction. Either the photon is completely absorbed or the photon is completely sent back. So if the incoming photon can be absorbed only when the electron can transit from its present orbit to any higher orbit. And if the energy difference is matching the energy carried by the photon, it is going to be absorbed. If it is not so, it will be thrown back or reflected back. So atom cannot keep the partial photon. Either the photon will be completely absorbed or it will be reflected back. So that's the idea of collision with photon. And when an atom, when an atom is having the excited electrons, and if that electron go from the high energy to the low energy orbit, the energy difference is again not kept by the atom. It is going to be released in form of again photon. Okay. So when you de-excite, then photon is released, and this is the mechanism by which light is produced. Okay. So a bulb or tube light or LED, they all are capable of creating light because of the excitation and de-excitation of electrons in the respective atom. And that de-excitation process is capable of releasing the photon. Okay. So photon is always byproduct of the energy difference of the two orbit when an electron jumps, okay, from the high to the low. We also have a concept of a meta state. So orbits are generally state, the finite state of energy values. But between the two finite state, we also have some, you can say, unknown state, which is generally called meta state, in which it is found that the stay is longer than expected. So generally, what I said that the electron will excite, but in no time it will de-excite. But meta states are those states in which they stay longer than expected. And we use these meta state to create a very famous phenomena in physics called laser. So laser is an acronym for the light stimulated emission of LA, light amplification by stimulated emission of radiation. Okay. So laser, what we do is we excite electron to the high energy, but it again drops to the some meta state where they populate themselves for some more time. And then from that meta state, they all jump together to the ground state. And because they all jump together, they release photon of exactly same frequency, close to exactly same wavelength, and that is how we create the monochromatic light. Okay, so that is possible because of the idea of meta state. Anyway, so that meta state, I mean, of course, one should be aware of.
Sir, I don't exactly understand, like the cluster of atoms within the same atom, or like a group of atoms, they sort of coordinate.
It is like, yeah, it is, of course, not one atom. It is a group of atom, but it is like pumping action. So we pump the electron from the ground state to the meta state in every atom, and with some design of material, we can actually create a predefined meta state. Okay, so that goes to the material science. There's a separate department of physics called material science. You can say chemistry also. So that the material science is neither part of physics or chemistry, it's a separate department. And when people are designing compounds, or mixture, alloys or something like, they're mixing things in a way to have a predefined metastate so that they can create more accurate monochromatic light. In fact, I think that 2012 or 24, 13, 14, something, after 12, I think 2012, the Nobel Prize in Physics went for the invention of blue laser. Now, blue laser means a light which is exactly blue wavelength, not a mixture of other wavelengths. It was, you can say, very accurate monochromatic light. Now, we do have blue LEDs, but what you think as blue, red, or those things are not monochromatic. They have a mixture of, you can say, photons, but the dominant one is red, so you see red. The dominant is blue, so you see blue. But when you create a sharp value of a blue light or whatever light, then it is really useful in various other technology, like etching the microprocessor chip on a silicon, chip, of course. So if you want to etch as small as possible dimension, you need as small as wavelength, and therefore the invention of monochromatic can make it possible. So it is having a huge application in some advanced technology, and therefore we're trying to achieve more and more. Anyway, this is not part of our board study, but one should be aware of. So
Okay,
we
sir.
need to know what is energy of excitation, what is ionization energy, uh, how atom behave, how atom interact with photon, how photons are released. So let's say when Bohr was performing this a hydrogen chamber experiment, in which the white light was sent through the hydrogen chamber, in which we had the H atoms, not H2 molecule. H atoms was there. So white light is coming from sun, and the sun energy, when passing through the hydrogen chamber, having some missing line. The line is missing because exactly those wavelength was carrying the energy equal to the difference of energy of the two orbit in H atom. And because that was matching the energy difference, it got absorbed. Because what I said, the collision of photon with atom is either full or null. So either you
Yeah.
take all the photon or you simply reject it. So the missing hydrogen spectrum, which we call H alpha, H beta, H gamma, H delta, the missing hydrogen spectrum was due to the result of excitation within the H atom by those photons. So when those photons were passing through the H chamber, they got completely absorbed by the atom, and therefore nothing was present on the other side. So the missing lines are the absorbed energy, and so you can at least say that the atom must have two orbits with energy difference equals to the energy of photon. That's why it got absorbed, isn't it? And
Yes, sir.
the missing of discrete value is also kind of manifestation that only certain energy values are present, not all. So that is how we came to know about the quantum behavior of atom. Understood?
Yes, sir.
So whenever something is missing, it means it is getting absorbed by the atom, and that absorption will result into excitation. Understood?
Yes, sir.
And everything which will get excited will also de-excite.
Yes, sir.
And therefore the same photon which got absorbed will be also released. But there is a difference. Absorption will happen in one way, but release will occur in many ways. So we need to understand how the absorption and emission will have a different behavior. Look at this. So imagine we have H atom with many orbits, and we have an electron in the ground state, and somehow a photon came with sufficient energy to excite it from here to here. So the energy of this photon was sufficient to go from 1 to 5. And if you remember, 1 to 5 is nothing but the E4, right? The fourth excitation energy. And how much is
Yes.
that? 3.4, 1.5, 8.85, 0.54, right?
Please. Yes, sir.
Which is 13.06.
Yes, sir.
And imagine I can add this by SC by lambda. Let's say this is energy equals to SC by lambda. I want to know what is lambda. So I come to lambda is this upon 13.06 nanometer. And let me calculate this. Just so it is like a close to 94.946 nanometer. I can say this is roughly 95 nanometer, right? Now
Yes, sir.
you will be given a reverse question. Imagine a wavelength of 95 nanometer is coming and it is getting absorbed by the H atom in its ground state. Good. So you know that if you convert this into energy, you will get to know it's 13.06. Now you know this is a famous number. We are going from 1 to 5, right?
Yes, sir.
So from the wavelength given, if you do the reverse engineering, you will come to know what is the energy value. I'm doing the reverse to get the question form. So what is happening? I know the electron will go directly to the fifth because the energy is absorbed completely. So you have to switch between those two orbits whose difference is equivalent of the energy carried by the photon. Okay.
Yes, sir.
Now, once you go there, then coming back is not controlled. So if you go there, you can come back from here in many ways. You may come back to here directly. That's quite possible. Or you may come from here to here and then make you another case, and then you may come from here to here, or then you may come from here to here. If you come here, then you can go from here to here, or here to here. And then again, I have to extend this line. Or if you go here, then you can go from here to here. You can see that from top, you can go to various level. From top, you can go to the bottommost, then second, bottom, third, or fourth. If you start from the second, then again you have multiple choice. You can go from directly here, here, here. And then if you start from one below, then there are two choices. Then this is the last choice. How many choices you have to come back? Can you count?
Yes.
You have 10 choices, right? Isn't it?
Sir, yes.
So the question is, if a wavelength of 95 nanometer is absorbed by the an atom in its ground state, then how many photon can be seen by the human eye? Or how many photons can be seen? Can you guess how many photons you can see? During the de-excitement process, how many? Because we don't have only one atom, we have infinite atoms. So because the number of atoms
Sir,
is
so
infinite,
like
so
10 types of.
no. Question is very interesting. How many you can see?
Sir, infinite.
No. I mean, not that way. I mean, how many different photon energy values you can see? That's it.
Oh.
So you can only see
Sir,
the
there
visible.
are.
You can only see the visible, right?
Yes, sir.
And out of the released photon, how many are visible? Can you guess? Okay, so I think you don't
Sir,
remember
2 to 3, 2 to 4, 2 to 5, 2 to 6. Those are visible ones, sir.
only these are visible.
Yes, sir.
This is called Balmer.
In Balmer, the first 4 lines are visible.
So here the Balmer, you can see we have only 3 photons creating the Balmer series, right?
Yes, sir.
So only 3 you can see, but of course 10 photon will be released, or you can say 10 different types of photon will be released, out of which only 3 photons will have the visible range.
Yes, sir.
Okay.
Yes,
So
sir.
many conceptual questions can be asked. You have to be mentally prepared that this is the visible UV. Rest are all are IR, right? The different types of IR.
Yes, sir.
Near, far, very far, very far, very far, and so on. So in each atom, you can see you can release UV rays, you can release visible and infrared. So what you cannot release in H-like atom? In H-like atom, you can't release the X-rays, you can't release the gamma rays, and so on. So these kind of rays are emitted from atoms with high atomic number. So only when you cross, I think, atomic number 40, not 40, I think, maybe 25 or 28, then you can start seeing the high energy radiation from there, from such atoms, because they do have the energy transition to an extent which falls in the range of X-ray or other areas. Gamma is having different mechanism of emission, so I'll discuss gamma. I have discussed this gamma in nuclear physics, right?
Yes, sir.
In
Sir,
Bohr's theory, what else we have to understand is something called collision of atom with particle. Yeah, you want to say something?
sir, no, sir.
So we have to study the collision of atom with particle. Then we have to understand the Rutherford alpha scattering experiment. That is one more concept, advanced concept. And then we have to understand the modified Bohr's theory, in which the nucleus is not much heavier than the orbiting particle or charge. Rather, their mass becomes comparable and things start changing. So these are three, four concepts that we need to understand. Like a binary charge concept we have studied in electrostatics, similar thing we have to apply here. And then we have to also
Okay.
understand uh, the board theory in different format. Okay, so those three, four concepts are there, which definitely I will discuss in the next class. Okay. So tomorrow we
Okay,
are
sir.
going to discuss the rest part of the board theory, right?
Yes, sir.
Okay, so I hope you got the some detailed idea of why and how the board theory works. Okay,
Yes, sir.
so I hope you can solve this question also in the examination with ease.
Yes, sir.
Okay, fine. So now since I have discussed the theory, you can start solving the PYQs from the board theory. Okay.
Sir, PYQs of both mains and advanced.
As of now, you solve mains first because the level of mains and advanced will be almost same in both theory. I mean, they will not create much difference to the question.
Okay, sir.
And then we'll, of course, in the revision lecture, you'll see there are some more challenging advanced subject tutorial of each years. Okay.
Yes, sir. Sir, the sheet for this chapter, sir.
I'll share the entire sheet of modern physics. I have the sheet actually. Just a moment.
Okay, sir.
I should
Sir, and I also think heat and thermodynamic sheet you have to share.
I think that I have shared. Have I missed it?
Sir, I'll check once again.
Yeah, I should check. I think I have shared. In case I have missed, just let me know.
Okay, sir.
No, I have shared. I have shared for sure. Just a moment. Let me check. Yeah, I have shared everything. You can just save all three hidden thermal lectures are shared actually.
Sir, not the this thing, sir. The notes, sir. The notes, all the types, and like all the type, like the note part and then the PPTs, all that I have, sir. The question part, sir.
Question part, which means the resonance sheet.
Yes, sir.
Okay, okay, fine. So just a minute. Mm, You can check. I think this is what you are asking, right?
Yes, sir.